Welcome to today's video, and today we'll be looking at the kinematic model of the robot. So, given that we've got a robot, we'd like to drive it along a certain path in a certain time. In order to do this, we must drive the wheels, but we need to use appropriate wheel velocities for it to follow this path we want. So to know what wheel velocities we need a kinematic model for the robot. Once we have this, we can then devise appropriate control schemes to control our robot. So the learning outcomes of today we'll be looking at how to transform between two coordinate frames. So the robot will have its own coordinate frame, and then we're going to have a global coordinate frame, for example the world or the room the robot is moving in. So we need to transform between these two relevant information. And then once we know how to do that, we can then derive our kinematic models for our different robots we wish to use. So we'll start this first video by looking at coordinate frames. So this is our scenario. So this is our robot here. We've got a differential drive robot, which we've got here. So it's differential drive, so we've got two drive wheels, one here and one here. And we have got an omnidirectional wheel here, and this is just going to support our robot. And we'll define a coordinate frame for our robot, and we'll call it, because it's with respect to the robot, we'll label it as R, this coordinate frame. So our coordinates are subscripted with R. And our x coordinate is going to be the forward direction of the robot along this direction. So this is our xr term. And then perpendicular to that is going to be our yr coordinate. Our origin for this coordinate frame we will have as the center point of the axle between the drive wheels. And this makes it convenient because this will be the point that the robot turns about. So that's our robot frame of reference. We also need a global reference frame, and we'll label this as I. So we've got an xi coordinate here and a yi. And this is our coordinates with respect to the world or the static global frame. So for example, if the robot is moving around a room, then our I is coordinates with respect to that room. If you notice, between the coordinate frames, we've got a displacement. So our origin of our robot frame is here. Our origin of our global frame is here. So we've got an XY displacement between these two frames. And we've also got a rotation angle theta labelled here between these two frames. We're not too worried about the offset, so I will explain that a little bit later. But we do need to consider the rotation between the two frames. So in order to consider this rotation, we'll consider two coordinate frames labelled A and B. So we've got our XA coordinate frame, our XA and our YA of coordinate frame A, and we've got our XB and YB of our coordinate frame B. The origins are aligned, and our rotation angle between them two is theta. And what we're going to say is, given that, we're going to consider a point in coordinate frame B, and we'll label that as P, point P, and then subscript B for coordinate frame B. And what we'd like to do is represent this in coordinate frame A. So it'll be the same point. It's the same point we're talking about, but it's now got different coordinates because the coordinates are with respect to A rather than B. So how do we go from this reference system and refer it to coordinate frame A rather than B? So what we're going to do is apply a transformation matrix given by this. So we've got our point P here in B, and we want to move it to, or represent it in coordinate frame A, and therefore we need some matrix that will apply that operation for us. So this is known as a transformation matrix. In this case, it's a purely rotational transformation matrix. We'll put a subscript on here to say we're going from frame B and we're going to frame A, so superscript A. So this is our matrix we want. So we don't quite know what this matrix is yet, so we're going to derive that. But what we do know is our point, which is represented by an XYZ coordinate in frame B and a corresponding XYZ coordinate in frame A. So given we've got this information and given we've got that information, we can work out what this matrix is. So we do that in stages, and the first thing we do is consider a point. So we'll consider a point in frame B with a coordinate of x, 0, 0. So if I just draw the y-axis in here, so this is our YB. Then our point in our x coordinate frame is it's x units along the x-axis. It's got 0 on the y-axis and 0 in the z-axis. So it's x, 0, 0. So if we look at this and transform or project these values onto our coordinate frame A, where this is going to be theta, then although it's got an x value in frame B, in frame A, it's going to have an x value which is x cos theta. Similarly, because of this rotation between the frames, this x value then translates to a y coordinate of x sine theta so it's in the y direction of frame A. So we can say a point of x, 0, 0 in frame B goes to a point of x cos theta, x sine theta, 0 in frame A. So in order to get that, what we need is this transformation matrix to look in a specific way. So if we put a cos theta in this place here, then that's going to give us cos theta times x, which is our x cos theta, which is what we want. This term, so this term and this term, they both multiply by 0. So you're going to have x cos theta plus 0 times this term plus 0 times this term. So because you're multiplying by 0, this value can be anything at the minute. So at the minute, this doesn't give us any information about what these values are going to be. So we'll just leave a question mark for now. But if we leave the cos theta in there, then that gives us our x cos theta, what we want here. We can do a similar for the x sine theta part here. So if we put a sine theta in here, this gives us sine theta times by our x here, plus 0 plus 0. So multiplying this line out by this line gives us our x sine theta. And then our final term, to get a 0 in this place, we have to have a 0 here. 0 times x to give us 0. And then potentially anything here for now because of the zeros. So by considering this point on the x-axis in frame B, we've managed to fill in some of our values in our transformation matrix. So the next step is we'll consider another point and try and fill in more of the matrix. So if I just escape this for now, go to paint. So if I draw a line, so if I draw the coordinate frames in here, so this is our XA, YA, this is our xb, yb, and this is theta. If we consider a point on the y-axis here, so in coordinate frame B on the y-axis, this has got a value of 0, y, 0. If we translate that point into our A coordinate frame, so put that along there, put that along there. So we've got theta here, so that means this is theta. So this means, if I change pen color, it means this length here is going to be y cos theta, and it means this length here is going to be y sine theta. So exactly the same argument, and we've just sort of projected that point into our A coordinate frame. One thing to note in this case is our y sine theta, so our x value here, is actually in the negative direction. So it's going to be a negative value, and therefore this is going to be a minus y sine theta here. So by considering the point 0, y, 0 in B frame, let's look at how that translates into the A frame. Given that, then that gives us, means we need a minus sine theta in here, and that gives us our minus sine theta times y, and a cos theta in here to give us our y cos theta, and again a 0 in this point, so we get 0 over here. So if we multiply that line by that line, we now get this. If we multiply that line by that line, we get this term. And if we multiply that line by that line, we get the 0. So that's filled in 2 of our columns in our transformation matrix. And then for our final column, we just consider a point in the z direction. So it's essentially out of the screen what we're looking at, and a point, so a point at x0, y0 and a certain value z, as you can see, because we're rotating about z, then that is going to translate to be exactly the same coordinates in coordinate frame A. So using the same argument, that fills in the final column in our matrix 0, 0, 1. So if we want to go from frame B to frame A, then we can multiply by this matrix. This is known as our rotational transformation matrix between frames B to frame A. So the next question is, what if we got a point in frame A and we wish to go to frame B? So we can use exactly the same arguments and derive this. We don't have to go to all that trouble though. So the easiest way to do it is mathematically. So given we've already derived going from B to A, then what we can do is just find the inverse of that. If we find the inverse of that, that is the same we're now going from A to B. You can use the standard mathematical formulas to actually calculate that. However, because of the symmetry of the problem, to calculate the inverse, all you're doing is changing theta into minus theta. So I'll just restart that to clear this. But because we're going from B to A, so we're going from B to A, then if I just scribble this out, if I can, try that again. So rather than go from B to A, if we want to go from A to B, what we do is put a minus in here. Okay, now cos of minus theta is the same as cos of theta, and the sine of minus theta is the same as minus sine theta. So when you actually work out the inverse, then this was our original transformation matrix, and the inverse just becomes this. So we don't have A, B, and we don't have coordinate frames A and B. We have robot frame R and global frame I. And we don't have an XYZ location. What we have for our robot is an XY location and a rotation angle. So we're working on wheeled robots in the plane. So it can move in X and Y, it can rotate about Z. So X and Y is our location on the plane, and theta is our rotation of the robot with respect to this plane. Now the problem with working with coordinates is because it's a mobile robot, then the robot will move over time, and then this changes the difference between frames. So if we try to use coordinates, every time the robot moved, we'd have to come up with a different transformation matrix to account for that. So rather than do that, what we do is work in terms of velocity. So rather than have an x there, we have x dot, if I can draw a dot on, y dot and theta dot. And therefore, rather than having a position matrix, a position vector, we have a velocity vector there. And by working in terms of velocity, we can then use our transformation matrices we've just derived. So we've got an x velocity, a y velocity, and an angular velocity. And you have to remember that angular velocities are expressed in radians per second. So do not use degrees per second, use radians per second for that. If we want to work out position, then if we know the starting position of the robot, all we have to do is integrate the velocity over time, and that will give us our displacement. So we either have a velocity of a robot, and that's defined in the robot's frame of reference. So for example, the robot might be moving 1 meter per second forward, or we have a global velocity. For example, the robot might be moving at 1 meter per second away from a table. Given we've got one or the other, we can then use the transformation matrices, the appropriate one, to then represent it in the other frame of reference. So it's a very quick example. We have a robot. So here's our robot here. It's moving at a speed. Now it's moving at a speed in the global frame of 1 meter per second forward. So it's 0 meters per second in the x direction. So it hasn't got any x velocity. So it's not moving in the x velocity. It's moving in the y. Got a y velocity in the global frame of 1 meter per second in this direction. And it is rotating at 3 radians per second. So it's turning as it moves. And it's currently offset, the coordinate frames between the robot and the global frame is currently 90 degrees. So it's rotated with an angle of 90 degrees, this robot. So given that information, what is the velocity of the robot in its frame of reference? So we can use our equation for the robot frame. It's just our rotation matrix times by our global velocity. So our global velocity goes in here. This is our rotation matrix with the angle. Our theta is 90 degrees in this case. So we put 90 in. Work this out and we get an answer of 103. So in the robot frame of reference, it's moving at 1 meter per second forward in the x direction. It's not moving sideways, 0. And it's rotating at 3 radians per second. So for a differential drive robot, we kind of need this value to be 0. It's a check that our calculations worked because it kind of slides sideways, a differential drive robot. So this is 0. It's moving 1 meter per second forward and rotating. If we go back to our problem, we can see in the global frame of reference, it's moving at 1 meter per second in the y direction. But in the robot frame of reference, it's moving at 1 meter per second in the x direction. And in both cases, 3 radians per second. So that looks to be correct. So this was a trivial example, but as problems become more difficult, this is where the benefit of the transformation matrix comes in. So that was a brief overview of coordinate frames. So what we'll move on to on the next video is looking at deriving the kinematic model for a differential drive robot.